the hidden elements shaping our world, powering our devices, driving the future, but at what cost? This is the story of rare earths, the unseen power behind modern technology. Hidden beneath the surface of our planet lies a collection of 17 extraordinary elements, rare earths. Though they remain largely unknown to the public, they are at the heart of modern civilization, powering everything from smartphones and electric vehicles to medical imaging machines, military defense systems, and green energy solutions. These elements are as vital to the 21st century as steel was to the Industrial Revolution. But despite their growing importance, rare earths remain elusive both in name and nature. Unlike gold or silver, which exist in visible, mineral deposits, rare earth elements are scattered across the Earth's crust, making their extraction complex and expensive. And while they are not as rare as their name suggests, their processing and refinement are among the most challenging in the world of industrial mining. The discovery and science of rare earths. The story of rare earths begins in 1787 in a small quarry in Ytterby, Sweden. A Swedish army lieutenant and amateur geologist named Carl Axel Arrhenius stumbled upon an unusually heavy black rock. This mineral, later named gadolinite, held secrets that would take nearly 2 centuries to unravel. At the time, scientists had little understanding of elements beyond those identified in the classical periodic table. But through careful isolation and chemical testing, researchers discovered that gadolinite was not a single substance, but a complex mixture of new elements. These were eventually classified as the lanthanide series, 15 chemically similar elements along with 2 additional elements, scandium and yttrium, which share similar properties. Each of these elements possesses unique characteristics. Neodymium and dysprosium form incredibly strong magnets, making them essential in wind turbines, electric motors, and high-performance headphones. Europium and terbium produce vibrant colours in LED screens and televisions. Lanthanum is critical in camera lenses and rechargeable batteries. Yttrium is used in lasers and superconductors, while gadolinium enhances MRI scans, revolutionising modern medicine. These elements do not exist alone but are found mixed within ores, often alongside radioactive elements like thorium and uranium. This makes their extraction a challenge, requiring advanced chemical separation techniques that generate toxic waste and environmental hazards. The mining and processing of rare earths. Unlike other metals such as copper or iron, rare earths do not form easily minable veins. Instead, they are dispersed in rock formations, meaning tons of material must be processed to extract just a few kilograms of usable rare earth oxides. The process begins with mining, most commonly in open-pit mines that strip away topsoil to reach rare earth-bearing minerals. These ores are then crushed and treated with chemical solutions to separate the rare earth elements. The result is a highly refined material that is further processed into oxides, metals, and ultimately high-performance materials for industry. But this process is anything but clean. Separating rare earth elements from ore produces enormous amounts of toxic waste. In Baotou, China, one of the world's largest rare earth processing hubs, there is a vast artificial lake filled with toxic sludge from refining operations. Heavy metals and acids leach into the groundwater, causing severe health and environmental issues for nearby communities. China's dominance and the global supply chain. For decades, China has been the world's dominant producer of rare earths, refining nearly 70% of the global supply. This dominance is not by chance, but the result of strategic government policies and massive investments in rare earth mining and processing. In the 1980s and 1990s, China aggressively expanded its rare earth production, offering low prices that undercut competitors and forced many Western mines out of business. By the early 2000s, the United States and other nations had become almost entirely dependent on Chinese rare earths. This dependence became apparent in 2010, when a diplomatic dispute between China and Japan led Beijing to temporarily halt rare earth exports. The move sent shockwaves through global markets, with prices skyrocketing and industries scrambling for alternative sources. Since then, nations around the world have sought to reduce their reliance on China. The United States has reopened the Mountain Pass mine in California, once the world's largest rare earth producer. Australia has expanded its production, while countries like Canada, Brazil, and even Greenland are exploring new mining opportunities. However, mining is only part of the equation. The real challenge lies in processing. While nations like the US and Australia mine rare earths, they still send much of their material to China for final refinement, a bottleneck that limits true independence. Rare earths and their role in green energy and technology. Rare earth elements are the silent force behind some of the most transformative technologies of our time. They are key to the clean energy revolution, enabling the development of high-efficiency wind turbines, electric vehicles, and energy-saving LED lights. The magnets inside an electric car's motor, for example, rely on neodymium and dysprosium, which allow for lightweight, powerful designs. Without rare earths, the electric vehicle industry would struggle to maintain the same performance and efficiency. In the defense sector, rare earths are equally indispensable. Fighter jets, submarines, missile guidance systems, and night vision goggles all depend on rare earth-based components. The US military has recognized this vulnerability, taking steps to secure alternative sources and stockpiles. The environmental and ethical dilemmas of rare earth mining. While rare earths enable a cleaner, more efficient future, their production remains an environmental paradox. Extracting and refining these materials creates significant pollution, often harming the very ecosystems that clean energy technologies aim to protect. In some countries, rare earth mining has led to deforestation, water contamination, and radioactive waste buildup. The human cost is also significant. Workers in unregulated mines face dangerous conditions, and some operations have been linked to forced labor and human rights abuses. The challenge ahead is to find more sustainable ways to source these critical materials. Recycling offers one solution. Currently, only a small percentage of rare earth materials are recovered from discarded electronics, despite the fact that millions of smartphones, laptops, and batteries are thrown away each year. If better recycling infrastructure were developed, it could significantly reduce the need for new mining. Researchers are also exploring new frontiers, such as deep-sea mining and even asteroid mining, which could one day provide an abundant supply of rare earths without harming terrestrial environments. The future of rare earths. As technology advances, the demand for rare earths will only continue to grow. The global shift toward renewable energy, electric transportation, and high-speed computing will place increasing pressure on rare earth supply chains. Yet the future does not have to be defined by scarcity and conflict. Innovations in material science, recycling, and synthetic alternatives could reshape the way we source and use these elements. Governments and industries are investing in supply chain resilience, ensuring that rare earths remain available for the generations to come. Rare earths, hidden in the earth, vital to the future. Their power, though unseen, is changing our world. Rare earths are the key to our technological future, but will we find a way to use them sustainably? Thanks for watching. Don't forget to like, comment, and subscribe.